Welcome back to ECE 320A. Today, homework number 9 is due. Try not to get your homework assignments mixed up and turn in 10 before 9, but hopefully everybody... It was a little unusual that I had 2 assignments posted at the same time, so hopefully you didn't get confused on that for too long. Homework 9 is on Bode plots. Homework 10 is on filters and two-port circuits, and that's due in a week. We have our final exam coming up a week from Tuesday, the 17th of December at 10:30 is when it starts. It's 2 hours long. In terms of final exam, there is some material to review on the D2L website if you're interested. And you seem to indicate that you were interested in a final exam review session. I need to maybe learn when that might be. I believe the 12th, which is a week from today, is reading day. You do not have a class a week from today, is the idea, I believe. Am I completely off? Your last day of classes occur a week from yesterday on Wednesday. And consequently, this is our next to last time we will be in lecture together in this class. So Tuesday will be our last lecture in this class. We will have our final exam a week from that date. I'm not sure how best to do this. I don't know if we want to pass around a sheet that indicates when you would like to have the exam review, if you have a preference for a day. Reading day is the 12th. Friday the 13th is the first day of finals. I don't know how many people have finals on that day. And then we could have the review session the day before the final on that Monday. I have another final late that evening, so I'm not sure what times you have available on Monday, but it would have to be before 5:30 on Monday, 5:30 p.m., unless we had it at 8:30 Monday night, but I think that's maybe a little late for a review session for an exam the following morning at 10:30. So, show of hands, reading day, 12/12, Thursday, sometime on that day. I'm not counting, but I'm scanning. I'm filtering. The Friday the 13th. Could we do more than one? Let's see a show of hands. Who's available or who would be okay on the 13th? I don't know what time. We would have to sort of decide on a week from Friday. You may have an exam on that day. Okay, and what about Monday, the day before the final? Okay, it's looking more like reading day. Well, maybe I'll send out an email or something, or set up a poll on D2L and you can vote that way. All right, let's get into what we need to talk about, which is, for today, filtering. How do we get different bandwidths? How do we scale those in terms of just not scaling necessarily the component values, but the transfer function itself? How do we scale polynomials? We'll be dealing with low-pass filters in this class. What if we want more filtering? We've talked about increasing the order of the filter, and we'll hopefully illustrate why it's nice to be using Butterworth filters. We'll then go into Butterworth filters. We'll look at a second-order active filter section, basically a little piece around an op-amp that realizes or implements a second-order filter, and we can then pick those parameters, the R's and C's around that filter, to produce Butterworth poles. And that's what we want to do, or that's what we'll hopefully convince you of today for this class, is that Butterworth filters are maybe better for certain reasons than just cascading a bunch of these first order sections that we've been dealing with so far in this class. We'll go through how we can calculate the filter order, and that's going to be based on how quickly you might want to roll off into the stop band. We'll try to present some design steps, the process that you can follow to design Butterworth controllers. And then we will get into our last topic probably of the semester, which is two-port circuits. And that's, I don't even know what chapter that is, but it has its own chapter. We're in 14 and 15, and then we go into two ports, and I don't remember whether that's before or after the Fourier series material. Let's look at filters, different bandwidths, and more filtering. Those are sort of the two phrases that I'm using to motivate the first two ideas that we will talk about today. First, let's just go back to, I hope, what you're very familiar with. And that is a first order normalized. And when I say normalized, that means that we have a bandwidth of 1 radian per second. If I then ask you to give me a transfer function that produces a low-pass behavior and it has a bandwidth of 1 radian per second and it's first order, what would you give me as a transfer function? 1 over s plus 1. Now, let's now look at that relative to some of these ideas that we will talk about in the next part of this lecture, but let's just look at the magnitude of that normalized low-pass filter. Let's look at the magnitude at the cutoff frequency. Which for a normalized transfer function where we have our cutoff frequency omega sub n of 1 radian per second, at what frequency am I looking to find the magnitude of that transfer function? That's at omega equal to 1, right? So now we're looking at this transfer function, h of s, but we want its frequency response, and we want the magnitude of that frequency response. That means that we are living on the imaginary axis. We replace s with j omega, and we want to find that magnitude when omega is equal to 1. We have a single pole in the complex s-plane. It's located right there at -1. We are now walking up the imaginary axis, and we are actually getting to this point, J1, and we go, what's the distance to that point? That will be the length of the denominator factor, and we'll divide that length into the numerator factor. That's really all we're doing. And I hope you can see that that length of the denominator factor from the pole to J1 is this square root of 2. It's the hypotenuse of a right triangle. But if we go through that, in the expression, we now have this magnitude in absolute sense, not in dB yet. We'll do that in a minute. But this is now the magnitude of the numerator. So I have a lot of vertical lines, and you have to know by context what each one is. The outer two are the absolute value signs. The 1 is the number 1. And then downstairs we have, I'm just having fun with vertical lines actually, vertical line J1 plus 1 vertical line. I'm just trying to be very clear as to what we're doing when we're computing this magnitude of the transfer function, which this transfer function is a normalized low-pass filter. Hopefully it's clear that the magnitude of a real number 1 is 1, and the magnitude of a complex number is just the square root of the real part squared plus the imaginary part squared. And we end up with 1 over the square root of 2. That's the magnitude of this low-pass normalized filter at the cutoff frequency 1. It has a magnitude of 0.707. 1 divided by 1.414. So this is now roughly 0.707. So we're at 70% of our DC gain at the cutoff. So we've actually rolled off a little bit in amplitude. We aren't right at 1 at the cutoff. But we're agreeing that this is now giving us the location that we define to be our bandwidth of a low-pass filter. if we wanted that magnitude in dB, then we're looking at 20 times the log, because these are voltages or currents. These are not powers. These are just voltages or currents that we're looking at in terms of transfer functions, or their amplitudes. They're not squares of amplitude, so we're taking 20 log of that amplitude. So we take 20 log, and this is base 10 log of H of J1. We want to know what's that cutoff frequency's magnitude in dB, and I hope maybe you already know what that's going to be, but that's now 20 times the log of 1 over the square root of 2. We just calculated what it was in an absolute sense. But the square root of 2 downstairs, let's do this in 2 steps. We now have the square root of 2 raised to the minus 1. And that minus, or that exponent now, because this is logarithms, comes out front. And now we have minus 20 log of the square root of 2. But we can rewrite the square root of 2 as 2 raised to the 1/2 power. And again, we can play with what we know about logarithms, and that exponent can come out front. Now we have minus 10 times the log of 2, but the log of 2 is approximately 0.3, and our cutoff frequency then is the minus 3 dB point, or the minus 3 dB frequency. And you might hear somebody say, oh, what's your 3 dB point? And they're probably saying the minus 3 dB. You're interested in what frequency do you finally reach a magnitude that's dropped off from 0 dB to minus 3 dB if you started with a DC gain of 1. If you started with a DC gain of 0.275, somebody might still want to know where are you 3 dB down from that. And that would be defined then as your cutoff frequency. Now, you may have heard of this cutoff frequency referred to in a different way. The cutoff frequency is potentially or sometimes called the half power frequency, or the half power point. And now we put on our pretend 2-year-old cap, and we say why. Why is that the half power? We have an amplitude, or a transfer function that scales the input voltage or current waveform by 0.707. So it cuts it down to 70%. But that's an amplitude. Power is what relative to amplitude? It's usually proportional to squaring the amplitude. So now if we look at that, if we now say, suppose we are given that this particular relationship for our transfer function was between an input voltage V sub I and an output voltage V sub 0. Now we can say that the power, which is, in very crude terms, V squared over R, that's now the power is telling us, or we now know, that the power is proportional to V squared. Which now, if we square both sides of that to get, if we divided by the same constant on left and right, then our signals, we would be interested in the power of those signals. We would have V naught squared over R is equal to this H of S V sub I of S squared, which is now this H squared of S V sub I squared. And if we divided by R on both sides, we now have power in our signal being adjusted by H squared of S. Well, that then says that if we're interested in the magnitude of our transfer function at the cutoff frequency, this again, remember, the reason why we're looking at 1 is because this was a normalized filter. And now we can plug in what we know that is equal to, which is 1 over the square root of 2, its amplitude. We square that, and we get 1/2. And that is then why some people might refer to that cutoff frequency as the half-power frequency. So if people start talking to you, or if in the interview they say, oh, what's the half-power frequency or frequency of that filter, you go, oh, he's asking or she's asking for the -3 dB point. And you can now find that, or you can at least talk to them about that, and you can draw sketches, you can draw Bode plots. And our straight line approximations are inaccurate at the cutoff frequency by that amount. If it's a first order factor, our actual curve for the magnitude is 3 dB below that cutoff frequency value that we're saying is 0, and then we're going down at -20 dB from that point. So we're just sketching in the Bode plot straight line approximations. But hopefully that gives you a better feel for cutoff frequency, its amplitude, it's 1 over the square root of 2 at the cutoff, and the half-power frequency. What if we wanted to, like I said the last time, we're not always living with a cutoff frequency of 1 radian per second. We might want that to be a megahertz, or we might want it to be 20 kilohertz. How do we get a different bandwidth? And if I just wanted a couple of, or a sentence, you might just say, oh, you need to frequency scale the transfer function. Let's figure out what that means. Our normalized transfer function for a first order low pass filter is this 1 over the quantity s plus 1. What if we actually want, instead of a bandwidth of 1 radian per second, what if we wanted a bandwidth, let's say, of 5 radians per second? Meaning now we're really saying, oh, our S new is 5 radians per second when our S old, or our original, was 1 radian per second. Last time we talked about how to frequency scale. And we said, oh, the new frequency, or the second frequency, whatever notation or subscripts we were using, we said just scale that by your frequency scaling factor, K sub f, from your old or original frequency. And so we can do that same thing here. But what we have in our normalized filter right now is the old S. So we want to replace that old S with a new S, and we want to do it such that it's in this relationship, K sub f S old, or we can simply say, oh, S old, wherever we see that in our transfer function, if it's first order, fifth order, 100th order, we replace S old with S new divided by K sub f everywhere, and that will translate our bandwidth to the new frequency. Our strategy then for frequency scaling, if I can get my pen to register, the strategy is to replace S in the normalized filter with this new term S over K sub f. If we then wanted to create a new transfer function that's low pass but now has a bandwidth of 5 radians per second, now we can simply scale our original normalized transfer function using this strategy. We can say k sub f is 5, and so if I said h sub s, I have now s is wild. S is now right there for scaled. That's now going to equal h of the original, or normalized. N is not new, n is normalized. So this is now our normalized filter. We now use S over K sub F everywhere we had an S before, if that notation makes sense. Meaning now we have 1 over, we had an S plus 1, but we replaced that S with S over 5. And now if we get a common denominator in the denominator, we have a ratio in the denominator that we can clean up by multiplying by 1, 5 over 5, or we end up with 5 over S plus 5. It maintains the same DC gain that our normalized transfer function did, and we have a bandwidth now of 5. And you could use either one. The one on the farthest right is in pole 0 form. The one before that is in time constant form. And what's your time constant? It's the factor that's scaling S, 1/5, or 200 milliseconds, or 0.2. That's your time constant for a low-pass filter that has a bandwidth of 5 radians per second. Questions on scaling? If you need to scale something, now you simply replace your S's everywhere with a new expression in S. S divided by K sub F. That's scaling. What if we wanted more filtering? So far, we've just been playing with first order. That's kind of boring. If we want more filtering, you can generically answer, oh, you need a bigger filter, or a higher order filter, or a larger order. What if we simply did something maybe seems logical, but maybe it's a little naive? Let's try to increase or build up a filter, a higher order filter, by just cascading or putting together these original first order circuits that we started with. So let's try creating a second order. We won't go very big very fast. Let's try creating a second order filter by cascading two of our original first order filters. What I'm saying is now if we want a second order filter, we had a first order filter that looked like that. We want more filtering. Well, why don't I just do this? Just double it, cascade it. What if I do that? Or that's now equivalent to something like that. Now we might say, okay, that looks clean enough and easy enough, and in terms of realizing that, you can just put these op-amp circuits back to back, put them in cascade. You now have a first order, which is an R and a C feeding back around an op-amp, and you have another one you can just add on to it, cascade them together. So you have this serial connection of low-pass first order filters to give you a second order. Now somebody goes, wait a minute. Have you changed something? You started with maybe a bandwidth of 1 radian per second. Now you've put two identical 1 radian per second low-pass filters together. Have you changed something? If you just did our straight line approximations for the Bodie plot, you're not going to see it. But let's look at the magnitude of this at what we might guess to be the cutoff frequency. So let's look at the magnitude of this second order filter at, we hope maybe what we've preserved is our bandwidth of 1 radian per second. So now we evaluate the magnitude of h of j1. We now have 1 over j omega plus 1 squared. Whoops. Where the omega is 1. Well, I know how to compute the magnitude of j1 plus 1. That's now 1 over, and so I'll do this maybe in stages. But I'm pulling that square out. So I'm looking at the magnitude of that complex number, and then I'm squaring it. What does that give me? That gives me 1 over the square root of 2 squared. Ouch. I wanted that to be what value? 1 over the square root of 2. Which one is smaller? 1 over the square root of 2 or 1 over 2? 1 over 2. So this is a half, and I was at 0.7. I was at 70%. Now I'm down lower. What in the... That's why you get paid the big bucks when you graduate, because you know this stuff, right? You know why this is happening. So if we simply sketched this, h of j omega, and now I'm not going to draw the Bode plot. I'm going to draw this in absolute magnitude terms. Here is our omega, and let's say this is 1 radian per second. Let's say this is now 1/2, and let's just, if you humor me, you'll say that that's 0.707. The first order filter looks something like that. But now we naively just combine these same first two or first orders to get a second order, and we ended up with something that goes through there. So now that's a second order. And what happened to my bandwidth? If I define my bandwidth to be the value of frequency where I go through 0.707, I've now reduced my bandwidth, haven't I? You could rescale that and move it out, and you'll have this gradual shape. But what we want to do is try to maintain a magnitude of 1 for as long as we can when we increase the system order, and then fall off and still go through that blue dot at 0.707, no matter what the filter order is. We don't want to change our bandwidth when we change our filter order. If you look at, so another way, if you don't like my sketch, you can actually look at a prettier sketch, figure 16. And now what you just told me is that this naive filter design to get a second order, I mean, you could rescale, couldn't you? You could frequency scale that and move that red curve over, but you still have this slow behavior, and you have a lot falling off in the passband. If you just keep this particular behavior, your minus 3 dB bandwidth is less than what we were hoping. What I hope this leads you to realize that we may need to do something a little different, a little more careful. So what we want is we want h of j1, the magnitude of our transfer function, to equal the same value, 0.707, 1 over the square root of 2, for all filter orders. And when I talked last time about maximally flat, and you know I have to put that in some kind of food context, right? That's just me. And you know now that that's probably flat as a pancake. Oh, pancakes. Butterworth, Mrs. Butterworth's. Oh, it's a Butterworth filter. That's right. That's what we need. We need the Butterworth filter. So this is demanding or requesting that we look at Butterworth and try to learn a little bit about the pole patterns that a Butterworth filter produces, or what are the poles associated with Butterworth filters, and they must be different than all of them just lumped at -1, because that sort of messed things up in terms of our cutoff frequency or our bandwidth. What we want to do then, if we were sketching h of j omega for Butterworth filters, now what we would have is we would still have, let's say that's 0.707 and here's 1. For the first order, it's going to look the same as what we just had. I'm sure that looks identical to the last blue curve, of course. Should be identical, okay? But now if we increase the order of the filter, what we want to do is we want to actually stay flat longer and then sneak through that point and then fall off more rapidly. So this is increasing in both of those cases. So as we increase the order of our system, this is, let's say, n equal 1, or first order. This black curve may be, let's say, n equal 4. That's a higher order filter. And if we do that, you will find that the magnitude of h of j omega for a Butterworth, I don't know how to, I was going to draw a pancake, but I better say Butterworth. For the Butterworth structure, you'd go, what in the world? What notation? That looks like pancakes. Oh, yeah, Butterworth. So Butterworth transfer function looks like 1 over the square root of 1 plus omega over omega c raised to the 2n, where n is the power or order of our filter. That 2n sort of, you'll see that many different places. Let's see if we can simply obtain a intuitive feel for where these Butterworth poles need to be. And I'm going to do that by building up a table. And I want you to take away this nice feel for Butterworth poles. Let's say this table now has 3 columns. The first column will be the filter order, and I'll call that n. Then the next column is the poles. I'm going to be talking about the angle between poles, the angular separation between poles. What's the angle? If I had a pole on the imaginary axis and I had a pole on the negative real axis, what's the angle between those? Between imaginary and real? 90 degrees, right? That's the angle between those poles. In the Butterworth, we will see that the angular separation depends on the filter order n by this ratio of 360 degrees divided by 2n. Now, granted, we're going to be looking at patterns that involve twice as many poles as we need, but where are our stable poles living? In the S-plane. Where do they live? If we have stable poles, where are they located? Left half plane. So if we have poles in the right half plane, we don't put those in our filter. We stay away from those and we only keep the poles in the left half plane. We're going to populate our entire S plane, but then we're going to neglect the poles in the right half plane. Is that okay? Because we're getting twice as many poles as we need with that 2n. So we'll neglect the ones that are in the right half plane. Then over here in the rightmost column is what we're interested in, which is the pole pattern. And remember, over here we're going to discard the poles in the right half plane. Now, you can already build this up for a first order filter. This now says that the poles are separated by 180 degrees, but where do you know a first order normalized, these are going to be normalized, so they're all going to be a distance of 1 away from the origin, all these poles. If this is now the S-plane, and I said draw the pole diagram for a low-pass filter with a normalized bandwidth of 1 radian per second, you would immediately do where would you put your pole? At -1. Now, the poles in this construction are, whoops, let me put these in blue since that's sort of our, and what we're going to do is we're going to neglect that one. But those poles are 180 degrees apart. Do you see that? And there's our pole pattern for a Butterworth. That one we already knew. Let's look at number 2. For a second order filter, and we want a Butterworth pole pattern, 360 divided by 4 says we have 90 degrees between our poles. And these poles need to be symmetric with respect to the origin. And I probably now have misled you with my earlier idea for getting you to think about separation of poles. If you have 4 poles spread in the S-plane, they're separated by 90 degrees, and you want 2 of those in the left half plane and 2 in the right half plane, none on the imaginary axis, how are they going to be distributed? If I didn't qualify that before, if I said I want 4 poles separated by 90 degrees, you could just put a pole on each of those 2 axes, right? So you have one at 1, one at J1, one at -1, and one at -J. There's 4 poles separated by 90 degrees. But how many stable poles do I have in that configuration? Just 1, don't I, at -1. So now I need to rotate that 45 degrees so that I get 2 in the left half plane and 2 in the right half plane, and my poles are still separated by 90 degrees. Is that okay? And they're all a unit distance away from the origin. So my Butterworth pole pattern for a second order now says that I have a pole here, another pole there, and I have these other 2 there that I'm not going to worry about. Those are unstable, so I neglect those. But here, I know that this is now omega sub n is equal to 1. I'm 1 away from the origin, and this angle is half of this total angle. This total angle is 90 degrees, and so now I can, just by trigonometry or geometry, I can compute those pole locations. They're minus 0.707 plus and minus j 0.707, right? They have a length of 1, and they're at 45 degrees up and down from the real axis. Is that okay? Now if somebody says, give me a second order Butterworth low pass filter, you know where the poles are going to be. Right there. Now, what if we make this bigger? What if somebody said, oh, I need a third order? Now what do we do? Well, first let's figure out how far apart in degrees our poles are. They're 60 degrees apart. Now I have an odd number of poles. Before in the second case, I had an even number of poles, and I had to split that angular separation right in half with that real axis. Now that I have an odd number of poles, every time you have an odd number of poles, you're going to have one pole at -1. And then the angular separation is easy to figure out where your remaining poles are at. Is that clear where you're going to plop these poles? You now have one at -1. And now they're all separated by 60 degrees. You just go up 60 degrees from here, and you're staying again one away from the origin. That's maybe not 60 degrees, but you can do better. You can bring your protractors if you need to the final, and your straight edges. How far apart or how far away am I from the origin? That length is still 1. And this angle right here is 60 degrees. And I also have the other 3 over here, but what do I do with those? I don't worry about them, do I? I just get rid of them. All right, you get the idea. Let's do it one more time. This is so much fun. 4. What if we now have a fourth order? $360 divided by 8. How about 180 divided by 4? 90 divided by 2? 45. All right. So now I have 45 degrees for my angular separation. But this is now an even set of poles. So I can't have one right at -1 anymore. But now I split that 45 degrees in half, and I go up 22.5, and I go down 22.5, and those are my first 2 poles. And if I could draw that accurately, I have a pole there, and then I go 45 degrees, and I go there. And then I go here, and I go there. And that's now my pole pattern. So this angle is half of the 45, and there is 45. And that's where all of these roots, if you look at one of your tables that has all of these pole patterns for the Butterworth poles, it's all because of this picture or these diagrams. Those poles will all allow the Butterworth poles to be falling on this Butterworth pattern. They're going to be symmetrically located with respect to the origin. If we have an odd number of poles, we always have one at -1. If we have an even number, then we don't have a pole at -1. And our angular separation is split in half to give us the first sort of pole in that second quadrant. Are there questions on that? Now we know a little bit about Butterworth filters. Let's learn a little bit more. Let's figure out how do we decide which order to use. So now we know something about Butterworth pole patterns. And what did we say about the passband behavior of Butterworth filters? let me not say than other, let me say than earlier, magnitude curve than earlier and that's the naive design that we had before with that second order. What's the magic word in the blank? Flat. So now these provide a flatter passband magnitude curve than earlier low-pass filters. We already know how to build up a first-order filter with an op-amp. That's an RC and feedback path. Here is a second order that will now allow us to put even powers of these pole factors together. First, we have negative feedback. That's now guaranteed by the way that's connected. Then we have a capacitor. And these subscripts are important now because that's going to be important in our derivation for the capacitors anyway. Then we have a resistor. And around that resistor we have a capacitor. And then we have another resistor. Those resistors are all the same in terms of their value. And here is now the input. Getting ahead of myself a little bit, if I wanted a third order filter, I'd just put this one in cascade with a first order, and then I have a third order. I just have to figure out what are my R's and C values for these pieces. And that's the whole point of this Butterworth design. The transfer function for this filter is H of S, and you could derive that by writing a couple of node voltage equations. What do you know about that voltage right there that I've highlighted in yellow? It's the same as V naught, isn't it? And we have V0 over there, and then we have another node right there. So you really only have 3 nodes. You can write 2 node voltage equations, one between the R's and one at, let's say, oh, you could write it at the at the inverting terminal node, and that's V naught. And now you have 2 KCL equations. If you do that, you will end up with H of S given as V sub 0 of S over V sub I of S equaling 1 over C1 C2 all over S squared plus 2 over C1S plus 1 over C1 C2. And I've already set my R's equal to 1. And then all I have to do is if I start magnitude scaling or frequency scaling, I just change those to whatever they end up to being. If I frequency scale, that R still stays at 1, doesn't it? Because the resistor is not frequency dependent. This is now a second order low pass, and we want it to now be such that it gives us Butterworth properties in the pole pattern, and we now know what those poles, where they need to live in a normalized setting. We know they're 1 away from the origin, and we know how to figure up their angles and where they're physically located just by some trig if we need to. If we now look at this denominator, we have an S squared plus, let's say, a B1S plus 1, if we normalized that denominator. If we compare the constant terms, that now says that I have 1 over C1 C2. That must equal what? This is now my normalized denominator. I've rewritten it in terms of just one coefficient, b sub 1, and upstairs in my circuit, I have some c's. I've already eliminated my r's by setting those equal to 1. But now that constant term in the filter needs to equal what to be normalized? It needs to be, I'm pointing at the 1 right there, but, well, I guess I can jump this high. I want it to be right there, don't I? I need that 1 to be equal, or I want 1 over C1, C2, which is the constant term in my transfer function, to be 1, and that will now normalize that transfer function's denominator, at least part of it. That now gives me a relationship between C1 and C2. If I know what C1 is, I can immediately calculate C2 from this relationship. C2 is just 1 over C1. Is that okay? Because I need both of those, when divided into 1, to equal 1. So they have to be reciprocally related. If I now look at the the linear term in both denominators, I can see that then B1 needs to equal 2 over C1. Meaning in the tables, you're maybe going to find a B1. And you now need to put that back into a filter. So now you say, oh, once I know B1, I now know C1. That's just 2 over B1. Is that clear? If I now had a fifth order filter that I wanted to build, I would put 2 of these together with the appropriate pole locations and 1 first order section. You can then concatenate or cascade these second order filter sections with the earlier first order filters or filter. Good, you didn't see that. I'm getting heavy-handed, getting so excited down here. Isn't this fun? All right, where were we? First order filter to yield higher order filters. And these higher order filters, or let me just say, the higher the filter order, the closer the magnitude response, or the magnitude characteristic, will be, changing my phrasing from when I wrote my notes. So the magnitude characteristic comes, the closer the magnitude characteristic comes to the ideal, magnitude characteristic. The ideal being, we want the passband magnitude to equal something, and we want the stop band magnitude to equal something. What are those somethings? They're different. And now you could just be in a digital class and get the right answer. Hint, hint. So now you have maybe a 50-50 chance of getting this right. What do we want the passband gain to equal in an ideal characteristic? 1, right? We want that to be the same as the input. And the stop band, ideally, we would like that to be 0. We're not going to get that, but as we increase the system order, we get closer and closer to that behavior. Let me just give you, you can look in the book how this is derived, but there's a formula that you need to know how to use to determine the filter order. So the formula for determining, and this is for a Butterworth filter, the formula for determining the order of a Butterworth filter is given by the following. N is equal to minus 0.05 a sub s over the base 10 log of omega sub s over omega sub p. And this is really just an approximation, but the approximation is pretty good as long as 10 to the minus 0.1 a sub s is bigger than 1. Which really says that if a sub s is in dB, which it is in this formula, a sub s in dB, the approximation is good as long as a sub s is less than minus 10 dB. So if a sub s is minus 20, this is a good approximation. This approximation for finding the order of our low-pass filter that we need to build. Now, what are all of these omegas and a's? If I sketch a curve, hopefully that will make that clear. Here is our low-pass filter shape. We can then identify our cutoff frequency, which this now is referred to as omega sub p for pass band. Then we want to be so far down by a certain frequency, which we are now calling the stop band frequency. And this is now our a sub s in dB. So maybe that's minus 30. This is this omega sub p is our cutoff frequency. Let's look at an example real quick, and then that will hopefully drive that point home. And notice in this formula that since I'm taking the ratio of omega sub s over omega sub p, it really doesn't matter what the units are. Those could be in hertz or radians per second, as long as they're both in the same units. Okay, if omega sub s is in radians per second and omega sub p is in radians per second, the two pi's cancel, and you could have been in hertz for omega sub s and omega sub p. Suppose somebody gives you the following problem. They say, suppose your passband frequency and or the cutoff frequency is 2000 hertz. And they want an attenuation in the stop band of minus 16 dB by a particular frequency, and in particular, maybe they say we want that to happen by 10,000 hertz. Is that a decade beyond f sub p? not, is it? But it's more than an octave, isn't it? How many octaves are there before you get close to 10,000? 4,000, 8,000, so it's between 2 and 3 octaves, isn't it? The distance between 2 and 10 in hertz. We don't have to know that. I'm just giving you that information just for your own benefit. But what do we have pictorially? Now we have some curve, and we were told here is our f sub p, and then we are told here is our f sub s, which is 10,000, and we want that value to be at least as small as minus 16. It can be minus 18, it can be minus 20. It's going to be probably less than that after we design this. But here, a sub s, we want it to at least be down by 16 dB. That's what we want. And if you wanted to see if the approximation was going to be valid, you could check 10 to the minus 0.1 to the minus 16, which is now 10 to the 1.6. So it's bigger than 10, isn't it? And we're going to say that's much bigger than 1. That's about 40. All right, now we can use our formula. In the system order, or the order of our Butterworth low-pass filter, is this unchanging constant, minus 0.05, and that's related to the square root of 0.1. That's where that's coming from in the derivation. Then we have our a sub s in dB, and we need to make sure that we keep the negative with it, divided by the logarithm base 10 of omega sub s, which we're going to just write it in terms of hertz, and over f sub p. That's really the log of 5, isn't it, in the downstairs. If we divide minus 0.05 times 16 by log of 5, we end up with 1.14. So now on the final you go, oh gosh, now I need to build a 1.14 order filter. We never talked about that. What do? Do we simply punt? We need to go up, don't we? We need to increase that to where we get to an integer value. And then we're over designing, but that's as good as we can do if we need minus 16 dB. We can't back off unless you can go argue with your boss and say, well, if we went with the first order, we would miss minus 16 dB at that frequency. Maybe we would get at minus 14 dB. And they would go, okay, that's okay. But for this class, you would say, oh, we need n equal to 2. So that now we need a second order filter in order to meet that particular design specification. Let's now write down the process, the steps for designing these filters. Here's a step-by-step, a cookbook way of finding a low-pass Butterworth filter. Here's a low-pass Butterworth filter design, and you need to be able to follow these steps. One is to determine the order of the filter. And if somebody gives you specifications, you can then plug those into that formula and figure out what little n is. Oh, you need a fifth order filter. Then you go and find the locations of your poles. You could rederive those, but they're already in a table. So you could find the normalized, and what does it mean when I say normalized? What's the bandwidth of this filter? If it's normalized, all of these poles are on this radius 1 away from the origin. So this now has a bandwidth nominally of 1 radian per second in the normalized filter. So find the normalized denominator polynomial in table 15.1 in the book. Step 3. Now, if this says it's 7th order, now you need to combine 2nd order sections and 1st order sections to give you a total of a 7th order filter. If you had a 7th order filter, you would need 3 of these 2nd order filters and 1 to give you the remaining order, a 1st order filter section. And you would have to assign all of those poles in each of those 3 2nd orders and in your single one. Single one's going to be easy, but you still need to find the R's and the C's. So the 3rd step is to combine 2nd order sections, that's filter sections, combine 2nd order sections, and this is actually figure 21 in chapter 15. With 1st order sections, let me just say with 1st order section, we're not going to build up any more than just one. We'll just use one of those with 1st order section, and that's figure 15.1. to obtain the circuit that you need, or to obtain the circuit realization. That's the structure of the circuit that you would need to build. Once you've found the number of sections and how many 2nd order sections you need, now you need to select or find or compute the capacitor values for each of those sections depending on what they're equal to in your table 15.1. So find the capacitor values in each, and they're going to be different for each section, in each of the 2nd order sections. The formulas are the same, meaning now if you have this polynomial, which you'll have several of these, if you had 3 2nd order filter or 3 2nd order sections, you're going to have 3 of these pieces, 3 of these polynomials. From this, you would say, oh, B1 is given in the table. That I need to make equal to 2 over C1. So C1 is 2 over B1, whatever B1 was. And you know that C sub 2 is 1 over C1. And all of the R's are 1. The next step, now you have a 7th order filter, let's say, that has a bandwidth of 1. And all of these capacitors and resistors are these funny numbers, maybe 2, maybe 1, maybe pi over 7, something, but they're not real, the real numbers, the real deal. So now what you need to do is you need to frequency scale to get the bandwidth that you want, and magnitude scale if you need to use certain, let's say, capacitor values. You want to use as many 1 microfarad capacitors as you can. So now you also magnitude scale the R's and the C's. Finally, we may not need to worry about this, but you might in your particular application, you might want to introduce an inverting amplifier circuit if somebody doesn't want the magnitude reversed or negated. So introduce an inverting amplifier circuit, or if they want to change the gain, maybe they want an overall gain of 6, you could use this inverting amplifier to do that. to give you a gain of 6. Introduce an inverting amplifier circuit if gain is needed in the filter. And this sort of decouples all of the pieces. Figure 15.9. And that one is the classical op-amp circuit. Relating the input and the output. Here's, let's say, the input resistance, and here's the feedback resistor. And what is VO over VI? That's minus R sub F over R sub I. Okay? In the remaining 4 minutes, we'll do a design. How's that? Let's look at a third order design. So now I'm skipping the very first step. I'm just saying we have the need to build a third order filter. But you could solve for what order you need based on particular design specifications. If you looked in table 15.1, you would find that for a third order denominator, it's factored into first order and second order pieces. You now need to realize a circuit that has this as its denominator. If you looked at these, do you now see where these are without even factoring those? What's your angular separation between the poles in a third order filter? 60 degrees. You have one at -1, and these others have to be 60 degrees away from that. And if you computed the roots of this, they are at -1/2 plus and minus j square root of 3 over 2. And what you're going to do is you're going to realize this first order piece with the circuit from figure 15.1. You're going to realize this second piece using that second order circuit that we just analyzed earlier or put down in terms of its transfer function. If we now look at the second order section, what's B1? It's hiding, isn't it? It's 1. So B sub 1 is 1, which means C1 is 2 over B1, which is 2. C sub 2 is the reciprocal of C sub 1, so it's 1/2. See what I'm doing? And now what do we have? We have a second order filter with these R's equaling 1. This one was C1, and that one's going to be equal to 2 to give us a bandwidth of, whoops, what am I doing? Drawing the wrong filter. I hope I didn't draw it that way before. I was trying to be quick and I got slowed down by being quick. Hint, hint for exams. Here's the second order piece. Here was C sub 1, which was 2. These were just 1. This was C sub 2, which was 1/2. And this is just a piece of the overall process. Now I need to cascade that with a first order section. What in the world am I doing? Okay, is that a little bit better? Wow. Hopefully you brought an eraser. Hint, hint, I guess, again for the exam. Here is now our first order filter. And we don't yet know what these are, but that needs to realize this first order piece that's 1 over s plus 1, isn't it? So we know what those are. But this whole combination so far is a normalized low-pass third order Butterworth. And it will be necessary, or did I even say what the bandwidth was going to be? Wow, I didn't. So maybe I'll start at that point on Tuesday. We'll maybe give this something other than a bandwidth of 1, and we'll see how to frequency scale those R's and C's overall to give us something that we need. We'll see you on Tuesday. And I need to